2.1 Basic Properties of Trees. So, in the previous module, we discussed what is a graph and we identified some common parameters that we may be interested in for a graph. Starting with Module 2 in 2.1, we're going to introduce this new class of graphs called trees. And then we're going to identify some parameters about trees. And for this module video in particular, we're going to talk about one special algorithm that's related to trees. So let's go ahead and start with our definitions as per usual. So starting off with our first definition, a graph that has no cycle subgraphs is called acyclic. Remember that we talked about what cycles were. These were, very informally speaking, was a graph such that if I can draw a circle and put however many vertices on that, that forms a cycle. The next definition I'm going to introduce is called the forest in a tree. A forest is any acyclic graph, that is any graph that does not have a cycle subgraph, whereas a tree is a little bit more specific. A tree is a connected acyclic graph. Another way that you could word this is that a forest is a union of trees. So forest, again, and tree, we're both acyclic. We don't have any cycle subgraphs, but a tree must be connected. That is, I only have one component for a tree. So whenever I'm talking about a tree or a forest, you're also often going to hear me say the word of a leaf or a pendant vertex. So this refers to a vertex that has degree 1. That is, it only has one neighbor. Next, I'm going to talk about a spanning subgraph, G prime. This is a subgraph of my original graph, such that the vertex set of my subgraph is the same as the vertex set of my original graph. So we talked about what a subgraph was. The definition was very similar. The only difference we have here for spanning is that I have the same vertex set. Before we didn't have that condition. I just needed a subset of vertices. Here I have the exact same vertices, possibly different edges. And lastly, we can talk about a spanning tree. Again, we know spanning means that I have the same vertex set. In a tree, it means that I am acyclic and connected. So a spanning tree is a subgraph that has the same vertices and is a tree, just as the name implies here. So just as a quick example, here I've drawn some random graph G. And I may be interested in some spanning subgraphs of this graph G. So, as one example, I may include this next one here, H1. Notice here, both of them have 6 vertices. I can assume that here I'm using the same vertices. But if I look at H1 and G, the edges are also the same from H1 to G as I've highlighted here. So this tells me that my H1 is a spanning subgraph. I covered all the vertices and possibly some of the edges. So I have my spanning subgraph. But notice that this is not a spanning tree, because here in H1 I'm obviously disconnected. I have 2 components. I have this Z-shaped component and this straight line component over here. I'm not connected. If I wanted a spanning tree, a good example of that would be something like here, H2. Again, I see that I have all the same vertices, and all the edges in H2 are possibly edges in G, as I've highlighted here. In this case, I can see that H2 has no cycles, so here we are acyclic, and we are connected. Hence, I have a spanning tree. So here we've introduced some common properties of a tree that we may be interested in. Now let's go ahead and look at our first lemma for today. So lemma 2.1.2. I claim that every tree with at least 2 vertices must have at least 2 leaves. In other words, if I draw any tree graph, then I know that there are at least 2 vertices, possibly more, that have degree 1. Furthermore, if I delete a leaf from an N tree, that is a tree with N vertices, then my result is another tree, but with just one less vertex. So let's focus on this first statement. I'm going to show you a proof sketch of our first statement here, and then we'll write it a little bit more formally. So our proof of the first statement, and here's a little bit of a sketch. So suppose that I have a tree, T. Here I'm just going to draw a box to represent any type of tree. We don't know what it looks like. I'm not being specific. I'm being very arbitrary here. And let's assume that I have a non-trivial tree. That is, I have however many vertices in my tree graph. And these may be connected in some type of way. My main condition is that these are all connected to each other, and I have no cycle subgraph. So if I look at this tree and any of the vertices, let's say I pick out any pair of vertices, let's call it U and V. So again, arbitrarily choosing any pair of vertices. By the properties of a tree, I'm going to say that between this vertex U and V, there does exist a maximal UV path. That is, there's some path in this tree that I've drawn arbitrarily that connects U and V. I know this is true because, well, trees are connected graphs, so there must be a path connecting these two. In fact, this path must be maximal. Remember, our definition of maximal says that there is no larger path here connecting U and V. So I have this here as a property of my tree. Well, this is just for any arbitrary pair of vertices U and V. I have a maximal path. I can imagine I can do this with any pair of vertices of my choice. So why not take a maximum UV path or a maximum path inside my tree? So I may have a maximum path, and this may be between some other pair of vertices. Here I just arbitrarily drew it. I have, let's say that I call this path P, and let's say that it's a maximum path. In this case, it is the longest possible path between among all of my vertices in my tree. So if I allow this to be a maximum path, let's go ahead and look at the endpoints. Again, we're being very arbitrary here. I have a maximal path, and if I look at these two endpoints, I'm actually going to go ahead and claim that these are my two leaves that are guaranteed when I have a tree. But why is that true? Well, let's look at this vertex on the far left that I've circled. Suppose that this has another neighbor. Let's say that's connected to this vertex here. Because if this is not a leaf, then it's degree at least 2. It must be connected to at least one other vertex. So suppose I do have this edge here. Well, if I do have an edge here, that tells me that I actually have an even longer path than P. I can take P and include this edge as I've highlighted here. So if my endpoint has an additional neighbor, then I can create another longer path. But this is a contradiction because we said P is a maximum path. P was supposed to be our longest possible path. So that tells me that my endpoint cannot have a neighbor, another neighbor to be exact, besides what's on the path. That means each of my endpoints only have one neighbor total. That is, they are of degree 1, which is exactly the definition of being a leaf in my tree graph. So this is a little bit of the sketch of the idea, for statement 1 at least. Just so that we have this a little bit more formally written out, let T be a tree. As I mentioned earlier, if I take any arbitrary pair of vertices that are different from each other, let's say U and V, then there exists a maximal non-trivial UV path. Again, because our tree is connected. If I create a path P and let it be the maximum path in T, that is the longest path among all of my vertices, not just a fixed pair, then since I chose a maximum and maximal as a result path, then its endpoints cannot have more than one neighbor, just as through that explanation I drew with the picture. As they cannot have more than one neighbor, they must be of degree 1, thus those two endpoints are each leaves in T. So this guarantees that no matter what tree I draw, as long as I have at least 2 vertices in my tree, there exist at least 2 leaves. And I want to emphasize the word at least. There could be 3 leaves, 4 leaves, however many that you want. And then for the second statement, you can try to prove this on your own time. I did include the proof for statement 2 in the notes, but this is the proof for statement 1. The next theorem I'm going to introduce is just some characterizations of a tree. So whenever we say that I characterize a tree, we had our definition of a tree saying it's an acyclic connected graph. But whenever I introduce this theorem and say that these are equivalent to saying that I have a tree and characterize my end tree, that means that these are considered also equivalent definitions. These are sufficient to say, if I follow this condition, then I am a tree automatically. So if I have any graph with n vertices, then the following statements are equivalent. T is a tree. T is connected and has n minus 1 edges. T has n minus 1 edges and no cycles. T has no loops, and for each pair of distinct vertices u and v, there is actually exactly one uv path. So the way that we would prove this, we're not going to go too deep into this. The proof is included in the notes for extra reference. The way that we would prove this is that I would say, let's go ahead and say A implies B, and I could say B implies C, C implies D, and then D implies A. So that's one way I might prove this. I prove that all these statements are connected to each other. They imply the next result. So definitely a proof that I recommend that you take some time to look at. It's actually a very nice and more or less quick proof as to prove this entire theorem. All right, so those were some characterizations of the tree. Let's talk about some more parameters of the tree. So for my next definition, if I have a graph and 2 vertices, u and v, the distance from u to v, here I use a notation d sub g of u comma v, or just d of u comma v. This is the length of a shortest uv path. In other words, the distance between u and v is what's the lowest number of edges does it take to get from u all the way over to v. If no such path exists, then I can say that their distance is equal to infinity. So here we have the distance between 2 vertices. And there are other parameters that we could look at for a tree. We can look at the radius of a graph, the diameter of a graph, the eccentricity. Those are also some very nice other things that I'm not including on this slide here. Particularly because I do want to get into this next theorem. So, how is a tree possibly useful for us outside of just purely graph theory and in the math world? So I'm going to go ahead and introduce yet again another algorithm. In this case, let's talk about the breadth first search, the BFS algorithm. BFS, we use this to find the shortest path between some fixed vertex of our choice and every other vertex in my graph. That is, I can find the distance between my fixed vertex to whatever other vertex I'm interested in. And then we're going to talk about this in a little bit of a computer science way, as usual. Let's go ahead and talk about what our input is. This algorithm takes in an unweighted graph, or digraph, with a fixed starting vertex u. And the idea behind this algorithm is that we're going to maintain these 2 sets of vertices that we're going to call R and S, where R represents R for reached, S for searched vertices. And then the way that we look at R is actually it's going to be a little bit of a queue list, where we look at the first vertex in that set as we go through this algorithm. For initialization, the way that we start this off is that we allow R to be whatever our fixed vertex is, S to be the empty set, and then clearly the distance between a vertex to itself is 0. If I want a path from a vertex to itself, I don't need to move at all. the distance is 0. The iterations of this algorithm state we search from the first vertex, say V of R, the vertices of V not in S union R, are added to the back of R and assigned a distance d of u comma V plus 1. And then V is transferred from R to S. And then we continue this iteration until R is empty. After we complete this algorithm, the output should be the distances between the fixed start vertex view and every other vertex. So let's go ahead and try to apply this BFS algorithm. So for this example, I have some type of graph here. Determine the shortest path between V1 and every other vertex of G. So I have this graph G with the vertices V1, V2, all the way up to V4, and then U1 and U2. And I'm fixing my vertex V1. Here I've already specified what do I want to be my fixed vertex. And we're going to go through our iterations and see how does this proceed. So for iteration 1, from our initialization step of our theorem, we let R be our fixed vertex, S be the empty set, and then the distance from the V1 to V1 is 0. And to help us visualize this, let me go ahead and color my vertices. So here I'm using a little bit of an orange glow to represent vertices in my set R, and blue to represent vertices in my S set. So right now S is empty, I don't have any blue vertices. So my iteration states, let's search from V1. That is, I look at V1, and I look at all the vertices that are connected to V1. In this case, I only have one vertex to search. So I search from V1, and then I can see and look at V2. Since V2 does not belong to R or S, that is, it's not colored in my picture, then I can go ahead and let V2 belong to R. So here I'm going to color it orange. And then I can assign its distance from V1 to be the previous distance plus 1. Or in this case, 0 plus 1, I get distance 1. After I assign its distance, I've searched through V1, so I can transfer V1 from R to S. That is, I can go ahead and change it from an orange color to a blue color. Now, as a result of my first iteration, I have that R is equal to V2, I reached V2, and I have searched V1. So I've completed one iteration. Now I can move on to my second iteration, and I'm actually just going to repeat the process. I move on to the next vertex in R, which happens to be V2. And just so that we have this down, again we said R was V2, S was just V1. Once again, I'm going to search from V2. So in this case, V2 has two edges that are untouched, or two vertices. And so, since these vertices are not in R and not in S, that tells me I can add them to R. So here, since U1 and V3 do not belong to S union R, I can add those two vertices to R. In other words, I can reach them with my current vertices. So now I'm coloring them in orange. And then I can assign them a distance of another plus 1. Or in this case, 1 plus 1, I get 2. So U1 and V3 have distance 2 from V1. After I assign distance, I can go ahead and transfer V2 from R to S, because I've already reached it, and now I have searched that vertex. So now I have that R is equal to U1 and V3, and S is equal to V1 and V2. Again, remember, we're using R to say what have we reached, and S to represent what have we searched. And now we can continue forth again with several other iterations. Notice here that in my R, let me go ahead to iteration 3, Now I went ahead and I want to search U1. Remember what I said earlier where R almost serves as a queue. That is first come, first serve. So in this case, I wrote down U1 first, so I'm going to search U1 first. So starting on iteration at 3. And this is just our results from iteration at 2. So once again, I search from U1. So if I search from U1, then I can reach U2. And notice that I'm not putting an arrow from U1 to V3. The reason being is that this vertex has already been reached. I don't need to reach that vertex anymore. It's been reached previously. So, since U2 is the only neighbor that does not belong to S or R, then I can go ahead and say we can reach U2 now. Furthermore, I can go ahead and assign it a distance of 3, like I have here. After I've considered all the neighbors of U1, that is all the neighbors of U1 are reached, I can go ahead and say that I have fully searched U1. That is, transfer U1 from R to S. I'm going to turn it blue. And now I have that R is equal to V3, U2, S is V1, V2, and U1. Once again, repeating my algorithm for iteration number 4. Notice here V3 was next in my queue, so V3 is the next vertex that we will search. So iteration number 4. Again, this is our results from iteration 3. If I search from V3, I'm looking for all the neighbors of V3 that have not been reached or searched. So in this case, the only neighbor of V3 that is not reached yet is V4. So since V4 has not been reached nor searched, I can add V4 to my reach set. Now I can go ahead and assign it distance. In this case, I will assign it distance of 3. I can actually count pretty clearly here from 1, 2 to 3. So V4 has distance 3 from V1. And after I assign it distance, I can go ahead and transfer V3 from R to S because I have searched the entirety of V3. Hence, now I have R is equal to U2, comma V4, and then my search S is the remaining vertices. Let's go ahead and do it again, iteration 5. Again, I go on to U2 because this is first in my queue. If I look at U2 for iteration number 5, again, this is my R and S set. I'm going to search from U2. But if I look at all the neighbors of U2, all of its neighbors have been reached or searched already. That is, all the neighbors of U2 already belong to R or S. Thus, there's nothing else for us to reach. Thus, all I had to do is transfer U2 from R to S. And now I have R is equal to V4, and then S is my other 5 vertices. Now I continue forth to the last vertex here. For iteration 6, I have my given information from earlier. I'm going to search from V4. But again, all of its neighbors are already accounted for. We've reached every other vertex. Hence, there's no other distances to assign. Thus, I can just directly transfer V4 from R to S, as I've done here. By doing that, R is now my empty set and S is all of my vertices. Or more casually, I've reached every vertex and I've searched every vertex here. Since my reach is now empty, I can terminate my algorithm. Remember that my conditions for termination was saying R is empty. In other words, what this algorithm does is that we go step by step and we try to see, can we search each individual vertex? And then we also take into account its reach. So to summarize what we've done here, let me clear up the screen. I had this graph and I can see the distance from V1 to every other vertex. So in other words, to get from V1 to U1, I had to go from a path from V1 to V2 and then V2 to U1, which is total distance of 2. One other thing I want to point out about this algorithm, the BFS, is that it actually gives us one other thing. Notice that these arrows I've drawn, that I can highlight through these edges here. If I redraw those edges, like this graph here, this actually gives us something really nice. This gives us a spanning tree of my original graph that also shows us the shortest path from V1 to each individual vertex. So for example, from again V1 to U1, the shortest path would have been from here, V1 to V2, V2 to U1, as we can also tell from here with a path of distance 2. Instead of going from V1 to V2 to V3 to U1, that would be a longer path. So as a result of this BFS algorithm, we have how far is each vertex from V1 and exactly what is that path. Furthermore, we can also find a spanning subtree for our given graph G. So this is the BFS algorithm, and this has a lot of very nice applications. In this one, it was a little bit longer, even though we had a smaller graph, but you can probably imagine that if I had a very dense, huge graph, then the processing speed of this algorithm may be significantly longer. This is also a good practice to see if you want to try programming this for some simple graphs. Alright, so that's what I wanted to cover for 2.1 on properties of trees. So that's all for 2.1. I'll see you in the next video.